This is a Physics AQA GCSE video, and it's all about required practicals for paper 2. We'll be going through both the content as well as past paper questions. The first practical I want to talk you through is the one relating to Hooke's law. Now, Hooke's law states that the extension of a spring is directly proportional to the force applied. And so if we look at this page taken from my revision guide, here we have our spring, which, remember, if you're at school, you'll have spent lots of time looking at springs in relation to Hooke's law. So you start with the original length of the spring, and then you add a weight. And as you can see here, we've added a 1 Newton weight, and obviously that spring will start to extend, and you can measure the length of that spring and work out the extension by taking away the original length. Then in our second experiment, we've added a 2 Newton weight. Obviously the spring gets longer, and so on and so forth. Eventually you get enough data so that you can plot a graph. You'll often be asked to plot this graph of extension versus the force. And in this portion of the graph, we say that the graph is directly proportional, and that's because it passes through the origin and it's a straight line. And what happens here is that Hooke's law is being obeyed because the extension of the spring is directly proportional to the force applied. However, it gets to a point where you add so much weight to your spring that it becomes damaged, it becomes deformed permanently, and we say that the limit of proportionality has been reached, so that's the end of the straight line. The elastic limit has been reached, and you'll see how the line curves, meaning that it no longer obeys Hooke's law. So I've stated that Hooke's law means that the extension of a spring is directly proportional to the force applied, and that is provided its limit of proportionality, the elastic limit, is not exceeded. They could ask you the meaning of the term elastic behavior. This refers to the ability of a material to revert to its original shape after the weights have been removed. And we'll go through a method in a past paper question. For example, though, our independent variable is the number of weights added, so that's what we're changing. The dependent variable, what we're measuring, is the extension of the spring using a meter ruler. And then our control variables, do be prepared to say what we need to keep the same. We need to have the same starting length of spring, the same diameter of spring, and the same spring constant. Now, in terms of what spring constant actually refers to, it's a measure of the stiffness of the spring. It's the force per unit of extension, and that's up to its limit of proportionality. And in terms of how we calculate it, spring constant equals force over extension. That's what this statement here is telling us. K equals F over E, and the units of everything, the force is newtons, the extension tends to be meters. So obviously the spring constant units are newtons per meter. If you have a large spring constant, it means that you need a large force in order to extend the spring. There's also a second equation, and that is that elastic potential energy equals 0.5 times the spring constant times the extension squared, because after all, remember that the type of energy stored in a spring is elastic potential energy. Figure 3 shows a child on a playground toy. The springs have been elastically deformed. Explain what is meant by elastically deformed. So this is the definition you need to learn. Elastically deformed means that the spring will return to its original length when the force is removed. A student investigated the relationship between the force applied to a spring and the extension of the spring. Figure 4 shows the results. Describe a method the student could use to obtain the results given in Figure 4 You should include a risk assessment for one hazard in the investigation. Your answer may include a diagram. So this is your standard investigation linked with Hooke's law. So it's when you add weights to the end of a spring and you measure the extension, but we just need to pad that out with more detail. So in terms of our method, step 1, set up a clamp stand with a clamp. Obviously you need something to hang the spring off. 2, hang the spring from the clamp. Use a meter ruler to find the length of the spring before any weights have been added. Let's have a look. What weights did they add? 1 newtons, 2 newtons, 3 newtons, 4 and 5. So our first weight is add 1 newton weight to the bottom of the spring. Measure the new length of the spring. To measure the extension of the spring, we want to do final length minus initial length. And then repeat for 2 newton, 3 newton, 4 newton and 5 newton weights. And then as I scroll down, I can see I've run out of space and I haven't answered the risk assessment. Always check back at the question to make sure you're answering all parts. So I'm going to actually have to pop it up here. Risk assessment, we only need 1 point. Spring could break and damage eyes. So how are we going to prevent that? We're going to wear safety goggles. So that's my full answer to ensure I've got my 6 marks. Which equation links extension force and spring constant? Force equals spring constant times extension. Figure 4 is repeated. Determine the spring constant of the spring. Use figure 4. So we need this equation. Let's sub in our values. I'm going to choose this point here because it's really easy to read off. 0.1 as the extension and 4 newtons as my force. So my answer is obviously 40. The student concluded the extension of the spring is directly proportional to the force applied. Describe how figure 4 supports the student's conclusion. For something to be directly proportional, it must pass through the origin. And secondly, that line must be straight. So we can see that that's indeed true on figure 4. The student repeated the investigation using a different spring with a spring constant of. Calculate the elastic potential energy of the spring when the extension of the spring was 20 centimeters. Use the physics equation sheet. So here's the equation we're using, which states that the elastic potential energy is half times the spring constant, K, times the extension. Just be careful with those units. We need it in meters. So I'm popping it in like that. And so when you've used your calculator, your final answer is 0.26. Now this required practical is all about Newton's second law, which states that force equals mass times acceleration. The unit of force is newtons, the unit of mass is kg, and the unit of acceleration is meters per second squared. I'm going to take you through past paper questions so we can really look at the methodology involved here. A student investigated the acceleration of a trolley. Figure 1 shows how the student set up the apparatus. So we have a trolley and card attached to a string which is linked with a mass holder, and then we have a data logger connected to a light gate. Before attaching the mass holder, the student placed the trolley at the top of the runway. The trolley rolled down the runway without being pushed. What change to the apparatus in figure 1 could be made to prevent the trolley from starting to roll down the runway? Look at the options. Move the wooden block to the left. So we're moving this block here further to the left, which means we'd in effect be straightening that runway, making it less of a slope. So that's highly likely to work. Shorten the length of the runway. No, that trolley will still start to roll. Use a taller wooden block. No, you'd increase the gradient and make it steeper. So that's obviously going to make the trolley move faster. The student attached the mass holder to the string. The string rubbed along the edge of the bench as the mass holder fell to the floor. Suggests what the student could do to prevent the string from rubbing. So yeah, the issue here is when that mass holder moves this way, obviously the string will rub against the bench. So one way we could stop that from happening is by adding a pulley to the edge of the bench. The light gate and data logger were used to determine the acceleration of the trolley. The student increased the resultant force on the trolley and recorded the acceleration. Figure 2 is an incomplete graph of the results. Complete figure 2. So we want to choose a suitable scale for the x-axis. So we've already got the acceleration done. Let's go through the resultant force. We need to go from 0.05 up to 0.25. So I've used up a really large portion of my scale. Plot the results, so I'm going to do that now. Draw a line of best fit. Describe the relationship between the resultant force on the trolley and the acceleration. So we can see it's a straight line and it goes through the origin, so it's directly proportional. Both of those need to be true for the relationship to be directly proportional. Describe how the investigation could be improved to reduce the effect of random errors. So the best thing to do here is to repeat the measurements, exclude any anomalies, and calculate a mean. Write down the equation linking acceleration, mass, and force. F equals ma. The resultant force on the trolley is this value. The mass of the trolley is this. Calculate the acceleration, give our answer to 2 sig fig. So sub in our numbers in the correct places. To solve for A, we do 0.375 divided by 0.6, and then check the wording of the question. We need it to 2 sig fig, so there's our final answer. The thinking distance and braking distance for a car vary with the speed of the car. Explain the effect of 2 other factors on the braking distance of a car. Do not refer to speed in your answer. Yep, it's already told us about that. So what sort of things would affect how far the car travels after you apply the brake until it comes to a complete stop? First of all, the condition of the tyres. Poor condition means less friction with the road and increased braking distance. Another factor which affects the braking distance is the number of passengers. The larger the number, the larger the mass, and this increases the momentum of the car, meaning that the braking distance also increases. Which equation links acceleration, mass, and resultant force? So it's F equals ma. The mean braking force on a car is this. The mass is this. Calculate the deceleration. So if F equals ma, A equals F over m. Sub in your values. So our deceleration is 4.5. Now this required practical is all about using a ripple tank in order to measure the frequency, wavelength, and speed of waves. So remember that frequency is the number of waves per second, and it's measured in hertz. The wavelength is the distance between 2 peaks or 2 wavefronts. It's measured in meters. And the speed, obviously how quickly the wave's travelling, that is measured in meters per second. So as you can see from this BBC Bite-Size page, so this is a ripple tank, a very typical setup. You'll have a motor and a power supply, and they're going to be responsible, together with the wooden rod, for creating the waves in your ripple tank, so creating the ripples. And then because you have a lamp shining through that water and you've got a meter ruler below, you can actually see almost like a trace of the wave below, and that will enable you to take all the measurements you need to find the frequency, wavelength, and speed of the waves in a ripple tank. So if you're keen for extra notes as to how we're going to observe those waves in a ripple tank, here's some info from my revision guide as to how we're going to measure the wavelength. Now, the frequency of the water waves, I've already said, is the number of waves per second. We can use the ripple tank by timing how long it takes for the waves to pass a particular point, and then use the equation frequency equals time taken over number of waves. It's also possible to use the equation frequency equals 1 over the time taken for one wave. In terms of how we're calculating the wave speed, we're going to use wave speed equals frequency times wavelength. But as with all of these types of things, it's much easier if we look at a past paper question. A teacher demonstrated some features of waves using a ripple tank. The teacher measured the time for 10 wave fronts to pass the mark. The teacher repeated this measurement 3 times and calculated the mean. What is the advantage of repeating measurements and calculating a mean? A more accurate mean will be calculated. The teacher's measurements for the time taken for 10 wave fronts to pass the mark were: calculate the mean frequency of the wave, give your answer to 2 sig fig, and it's worth 5 marks. So frequency is given by 1 over time. In order to find the average time, we need to add up these values and then divide by 3 to give us 8.1 seconds. Put that into your calculator to get 1.2345. They want the final answer to 2 sig figs, so that's 1.2. Please don't overly stress about these calculations. You'll tend to have to do either unit conversions or be careful with your decimal places or sig fig, but they are doable. In a different investigation, the teacher wanted to determine the speed of water waves in the ripple tank. The teacher did not measure the wavelength of the wave. Explain how the teacher could determine the speed of the wave. So as with so many physics questions, we want to use an appropriate equation. So how do we find speed? Well, speed equals distance over time. So the first thing we need to find is the distance travelled by the wave. And how do we do that? Using a meter ruler. Then we want to measure the time taken for one wave. Using a stop clock, and then finally sub in our values to speed equals distance over time. This required practical is all about reflection and refraction, so I'm going to take you through what each of these words means. So if we start with reflection, in essence that just simply refers to a ray bouncing off an object. So if I draw a plane mirror down here, we know it's a plane mirror because of this hashed line. We need a normal drawn at 90 degrees. And the ray coming in, it's a light ray. Because it's coming in, we call it the incident ray. And remember, the angle between the incident ray and the normal is known as the angle of incidence. Now, what's true in reflection, there's a law which states that the angle of incidence equals the angle of reflection. So when I draw my reflected ray, the angle of reflection needs to be the same size as the angle of incidence, so we can make that point there. If we now look at the formation of an optical image by a plane mirror, this is the object that the person is viewing, and this particular diagram is all about working out where the object will appear to the person. So it's actually possible to draw our incident rays. They're reflecting off our mirror. There's our normal line drawn at 90 degrees. And as you'd expect, the angle of incidence here is the same as the angle of reflection. So those light rays will be bouncing into the person's eye. And it's important that you're aware that the image produced will be, first of all, the same size as the object. Look, those light bulbs are the same size. It's going to be the same distance from the mirror as the object. So if you were to measure these distances here, they would be the same. And the third point to make is that that image would be virtual. And what we mean by a virtual image is that it can't be displayed on a screen. So to all intents and purposes, this light bulb appears behind the mirror here. If we now move on to think about refraction, refraction is very different from reflection. Refraction is a change in direction of waves as they travel across the boundary from one medium to another. And what's responsible for refraction occurring is a change in the wave's speed. So if you're at school, you may have done this experiment. Here's our glass block. There's my normal, drawn at 90 degrees. Here's my incident ray. It's a light ray. And as such, this is my angle of incidence. Now, if refraction didn't occur, you'd expect that ray to continue in this direction. But the ray is moving from air to glass, and as such, it's going to change direction as it crosses that boundary. It's actually going to slow down as it enters the glass, and that's going to cause that ray to change direction towards the normal. So as you can see, this ray has come closer to the normal. It hasn't stayed unaffected, it's moved closer to the normal like this. There's my angle of refraction. We need a new normal here because we're about to go from glass to air again. This time, as the ray enters the air, it speeds up, and so it's going to change direction again, this time away from the normal. And actually, we need to try and make sure that that ray is parallel to this incident ray here. Try and make those as parallel as possible. From my revision guide, you can see that diagram. It's drawn more nicely than the one I've just constructed. If the ray comes in at 90 degrees, i.e. it follows the normal line, it won't be refracted. It continues straight through without changing direction. You can also see this diagram if we look at it from a wavefront point of view. So I've just shown you how to construct the orange line, but if we were to add wavefronts, this is what would be happening. And then lastly, I just want to show you, if they ask you to describe a method to investigate the refraction of light at the boundary between air and glass, these are the kind of steps you need to be providing. We need to place a glass block on a piece of paper and draw around it. We use a ray box to shine a single ray of light through the glass block. We make a note of where that ray of light enters the glass block and where it leaves. Then we join those points. We add a normal so that we can actually measure our angle of incidence and our angle of refraction. Make sure you're mentioning the fact you need a protractor to do that. And then we can alter the angles of incidence to produce new angles of refraction. And I'm going to show you a past paper question now that deals with this. A student used a ray box to shine a ray of light through air into a glass block. The student investigated how the angle of refraction varied with the angle of incidence. Describe a method the student could have used to obtain the results in table 1. Your answer may include a label diagram. Now, I don't usually like drawing because I can't draw, but I think this could be a good place for that. So I'm going to show my glass block. There's my normal. Here's my incident ray. So there's the angle of incidence, the incident ray from the ray box. And then here's the refracted ray, so the angle of refraction. And remember, we need to measure those angles. We need to describe all the apparatus. So I'm going to say using a protractor. And actually, my diagram's pretty good, so I'm going to get loads of marks for using a ray box to shine light into the glass block. I've labelled my incident ray, so I get a mark for that. I've labelled my refracted ray, so I get a mark for that. I've shown my normal at 90 degrees to the glass block, so I get a mark for that. And I've even said that I want to use a protractor to find the angle of incidence and the angle of refraction. So there's actually 2 marks for that. Just make sure that we change the angle of incidence. That will be our independent variable, so we can measure a large number of angles of refraction. But yeah, this is the one time where a label diagram is going to be your best friend here, because it's really saved me a huge amount of time describing how I've set up that glass block. Figure 2 is an incomplete graph of the results. Complete figure 2 using data from table 1. We need to label the axis, plot the remaining data, and draw a line of best fit. Let's start with our axes labels. Here's our angle of incidence on the x-axis in degrees. Here's our angle of refraction, also in degrees. So So I've labelled the axis. Now I need to plot the remaining data. So I'm plotting this point here, 40 and 19, 50 and 23, 60 and 26, 70 and 28, 80 and 29. There's my line of best fit, so I've done everything I need to get those 4 marks. Complete the ray diagram in figure 3. To show the reflection of light from the surface of a plane mirror, you should draw the normal line and the reflected ray. So the normal line, as I've said previously, is the line drawn at 90 degrees. It needs to be dashed. And then the law of reflection states that the angle of incidence equals the angle of reflection. So we need to make sure that our angle of reflection here looks similar to the angle of incidence. So use your protractor there if you're not sure. 2 students investigated the reflection of light by a plane mirror. Figure 4 shows the different equipment the students used. We explain 2 ways that method A is better than method B. So the first thing to point out is the fact that in method A, the protractor has been drawn on the paper versus protractor B, where you have to keep moving the protractor. And this gives you the advantage of meaning that your angle of incidence and reflection is more likely to be accurate in A. And secondly, if we look at the ray, with the laser, it's just a single beam of light versus the ray box where you can see that ray diverging, meaning that again, A will give you a more accurate representation of the angle of incidence. This required practical is all about how we can investigate how the amount of infrared radiation absorbed or radiated by a surface depends on the nature of the surface. So we're really talking about the effect of colour and whether that surface is matte or shiny. To begin with, let's understand what we mean by infrared radiation. Remember, you've met it in the waves topic. It's a type of electromagnetic wave. Infrared radiation is both absorbed and emitted by all objects. And one thing to be aware of is that the hotter the object, the more infrared radiation it emits. So if we now talk about colour and the type of surface, you'll find that dark matte surfaces, they're going to be good emitters and good absorbers of infrared radiation. So my hair is basically black, and I do notice that on a hot day my head feels very hot because my hair has absorbed a huge amount of infrared radiation. It's also giving off a lot of infrared radiation. Think about in countries like Greece, why are all the buildings painted white? Because white, and I'm just going to pop shiny here, that's obviously not relevant with the building, but white shiny surfaces are poor emitters, poor absorbers of infrared radiation, and they're good reflectors. And to work out how well something is emitting infrared radiation, remember we could use a thermometer or an infrared detector in order to measure that. Infrared waves are transverse waves. Complete the sentence. In a transverse wave, the direction of oscillation is something to the direction of energy transfer by the wave. This is a definition you need to learn off by heart. Oscillation means the same as vibration, and in a transverse wave that occurs at right angles or perpendicular to the direction of energy transfer. If the question had been about longitudinal waves, you would have substituted perpendicular for parallel. A student investigated how the colour of a surface affects the rate at which the surface emits infrared radiation. Figure 1 shows some of the equipment used. We've got both a silver and black coloured flask, as well as a kettle of cold water. The student wrote the following hypothesis. The black coloured flask will emit more infrared radiation than the silver coloured flask during 10 minutes of cooling. Describe a method to test this hypothesis. So obviously the colour of the flask is our independent variable, so that's what we're changing. Now, in terms of our dependent variable, we're looking at how much infrared radiation is being emitted. I think the simplest way of measuring that is looking at how fast that flask cools down. So we can measure that using a thermometer. We're going to find the initial temperature and the final temperature after 10 minutes. You could also use an infrared detector, but I think that's less commonplace, and I think let's use a more straightforward apparatus here. So clearly, in terms of the method, we need to boil water in a kettle. After all, they've provided us with a kettle. Then we need to make sure we are controlling how much water we're adding to each flask. So I'm going to choose 100 centimetres cubed of water is added to each flask. Then we want to insert a thermometer and measure the initial temperature. We know we need to record the final temperature, so we are going to use a stop clock to do that. After 10 minutes, record the final temperature and calculate the change in temperature. We can infer here the greater the temperature change, the more infrared radiation that has been emitted. So we're really testing our hypothesis. And as always, we want to repeat and calculate an average. When will the flasks emit infrared radiation at the greatest rate? Give a reason for your answer. So it's going to be in the first minute, and that's because you're going to have the greatest temperature difference between the hot water and the surroundings. So you'll have the greatest rate of cooling. Another student investigated the absorption of infrared radiation by different surface colours. The student filled 4 hollow metal cubes with cold water. Each cube was the same size but a different surface colour. The cubes were then placed the same distance from an infrared heater. After 10 minutes, the student measured the temperature increase of the water inside each cube. What was the dependent variable in this investigation? The dependent variable, remember, is what you measure. So just have a look. We're looking at the temperature increase, aren't we? You must learn what your variables mean. Table 1 shows the results. Give 2 conclusions that can be made from the results. So we can see that the greatest temperature increase has occurred with the matte black. The lowest temperature increase has occurred with the shiny white. So I've made the conclusion that matte black surfaces absorb more infrared radiation compared with shiny white, and that's responsible for the greater temperature increase we can see compared with the lower temperature increase with the shiny white. And actually I've written 2 points there, so that will get me 2 marks.